Okay. Uh, okay. At the risk of you going deaf. Okay, it's the end of the day. I'm sort of hearing myself. That's fine. Okay. Too much? Okay. 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 So it's the end of the day. We're all tired, which means that feel free to ask any question, meaning you dozed off, didn't follow me, ask me, because chances are you're not the only one dozing off. Okay, so okay, so just a recap of what we did yesterday. We were discussing pressure in active. Eventually, wanted to reach active systems. We got there, and the setup which we were considering was uh, a system confined by potentials on the two sides. And one thing that was implicit, and I should have stressed, is that I was assuming that the system is homogeneous. Okay, so it's a homogeneous system. There's no gradients. You could drive, and I understand why it was confusing to people, because the standard way of driving a system out of equilibrium is by imposing some external gradient. But we're thinking about active systems, so that doesn't apply there. And we have several expressions for pressure. We had the one that comes from thermodynamics. And the outcome of this expression, by definition, is that pressure is an equation of state. Okay, the minute that you have this definition, you use it, pressure is an equation of state. The other expression was related to the flux of momentum. And I remind you, this is the angular brackets denote an average over the steady state. And you could take it somewhere in the bulk of the system. Say x equals L over 2 if this is 0 and this is L. And this is, again, by definition, a bulk quantity. And therefore is an equation of state. Okay? The other definition was what I called a mechanical definition. dx of v. And that's, looking at it, that's not clearly a bulk quantity. The density depends on the potential depends on the potential. So it's not an obvious, clear case that this is an equation of state. Now what we saw was that in equilibrium, automatically PE is equal to PM. And the reason for that was the Boltzmann distribution. Okay, so Boltzmann led to this result. We used explicitly the Boltzmann weights. Then we saw that either we're at equilibrium or out of equilibrium. If we have momentum conservation, and the only sink of momentum is the wall, okay, wall only sink, then we have automatically that PM is equal to PP. Okay? Which implies that in equilibrium, all these guys are the same. Okay, so we identified that maybe if we look at the non-equilibrium state system with no momentum conservation, maybe something interesting is happening. Okay, and what we did was sort of defined a simple model. Okay, and the simple model, I won't repeat it. It's just active Brownian particles. I think it was discussed enough today. But essentially what we had in mind were ellipses that are moving with a velocity v. They have some diffusion of the center of mass. And when they enter the wall, they experience the potential. And the direction, because it's an ellipse inside a wall, causes inside the wall, induces a torque on the particles. Okay, so that's a simple model, ideal gas, no interactions, nothing. Okay, and what we did was we calculated, we didn't calculate, I sort of threw at you an expression for the pressure, and given the pace that I'm advancing, I'm going to keep it at this level. And the expression for the mechanical pressure, again, we definitely can't use this one. No conservation of momentum. This one at the moment doesn't make any sense. So this is the only definition that we can use. And we got, it's an ideal gas, so everything better be proportional to the density. And then we had the translational diffusion divided by the mobility, which is also known as KBT. Then we had V squared divided by 2 mu dr, which is again what you would guess by dimensional analysis. This is the diffusion coefficient of these guys, in the bulk. We discussed that, divided by mu. And then we had an extra term which was less trivial. And looking at it, it wasn't obvious that it's independent of the potential. Specifically, this guy depends on the potential. The probability of finding the particle at position x with angle theta definitely depends on the potential. And the outcome that I finished with yesterday was that indeed this guy depends on the potential. So I want to know PM, the mechanical pressure. You have to tell me exactly the potential that's acting on the system. Okay, so I just want to, because I sort of rushed through it, I want to sort of give the comments. So the comments. One, when V is equal to 0, we're back to equilibrium. Okay, by definition. And then we have PM is equal to rho 0 KBT. Okay? V squared over 2 dr is our effective diffusion coefficient. And if we have no torques, okay, let me skip it. When we have no torques, this is the pressure. And some people, this is just a wording, some people call D effective divided by mu the effective temperature. Okay, it's words. You might like it or might not like it. When there are no torques, we have an equation of state. So PM independent of V of x, which is great because this means that for this class of models we have an equation of state. And that's a very useful thing to have. Okay? And again, when there is torque, no equation of state. Okay? And in fact, just to sort of hammer this, and again, I'm skipping the calculation, you can actually do an approximate calculation, which I'm going to skip. There's a small, really tiny approximation done here. But if you take a quadratic potential for x larger than L, so it's just a half a harmonic oscillator, and lambda is the strength of the harmonic oscillator, and you take the torque just of a solid ellipse, so I'm going to write it as lambda kappa sine 2 theta. I remind you the sine 2 theta is what you expect. This is the angle theta, and if the ellipse is just pointing into the wall, there's no torque. If it's normal to the wall, there's no torque, and anything in the middle that's being pushed, rotated. So you can calculate this actually with a simple model, but you can guess that this is the leading order behavior for an ellipse. Okay, so lambda is the strength of the potential that comes directly from the potential, and kappa is the measure of how asymmetric the ellipse is. Okay, I'm not going to even bother with the expression, but it's how asymmetric the ellipse is. Okay, if it's 0, it's a circle. If it's not 0, it's an ellipse. Okay, and the calculation is done with dt is equal to 0. Again, a really tiny approximation, but I want to write down the expression because it's pretty clean, and I'm going to draw it. Okay, so this is a closed expression for the mechanical pressure in this case, and you can check that you could take the limits when kappa goes to 0. I'm going to leave it as a small exercise. You recover the equation of state over there. Okay, you just expand this guy, and you can, okay, if you're very quick, you could do it while I'm talking. Okay, but otherwise, you can see that as we change the strength of the potential, there's a very strong dependence on the strength of the potential. Okay, and I want to draw the result just to hammer in one thing. So if I draw 2 mu dr p over rho 0 v squared. So why am I drawing this? This quantity is 1 in the case that I have no torque in the system. Okay, remember this guy is 0. So that quantity is 1 when I have when I'm dealing with circles with no torques. Okay? And what I'm going to do is draw this as a function of kappa lambda. And what happens is that this changes between 1 and it goes very sharply to very close to 0. So the whole point of this discussion is that it's changing not by epsilon or by something small. It's changing by something of order 1. You can make a tremendous change in the pressure by changing the strength of the potential. Okay? And the more shallow the potential, the higher the pressure. Yes? What is mu r? Yes. Very good, thank you. Mu r is 1. Okay, I got rid of it in my notes, but when I took this equation, I left it in. It's a rotational mobility. Okay? Okay, thank you. Yes? The first term should be? No. No. Okay? Okay, good. And you can see when there's a scale of the strength of the potential where things change in a dramatic way. It's given by the rotational diffusion divided by the asymmetry of the ellipse. Yes? What? Kappa is this guy. You see, I'm also tired, so it's very good that you're asking. It's this guy that's telling you how asymmetric the ellipse is. When it's 0, it's a circle. Okay? Yeah, I didn't want to write it. Its kappa is 1/8 a squared minus b squared, where this is a and this is b. Okay, sorry. So you have to be really alert because I'm also tired. Okay? Yes. Yes. So? No. Okay, so I set the translational diffusion to be 0 here. Okay, so I'm losing this term. Okay, just for calculational reasons. Yes. No, so what I'm saying is that if you want to know the force exerted on the wall, okay, I don't know, we'll have to discuss what it even means to look at this quantity in the bulk. Okay, there's no momentum of conservation in this problem, so you better define what this guy is. Okay, and we'll get back to it later, hopefully today. Okay, so this doesn't make sense on the face of it. The only thing that right now makes sense is PM. Okay, and that you have to tell me the potential. Yes. Well, then you have the argument that I gave you before, which you have to beat. Okay, if the only sink is the wall, and I have momentum conservation in the bulk, then I have PM is equal to JP, and that's it. So you have to tell me how you beat that. These results are in 2D. You can find versions in 1D. Okay. 2D, the same result to go through easily. Okay. Just think about, don't complicate things at the moment. Just flat walls. Okay, we can complicate things later. Okay, just a flat wall and you have a homogeneous bulk. I think we're all good to go. No? Okay, we can discuss it later. Okay, yes. No. Okay, just expand this. You'll get rid of this kappa and you're back to this guy. Okay? Good. Okay. So again, things change by a lot. Actually, the pressure goes down to almost non-existent. And again, a weak potential, soft potential, it's a strong, large pressure, and a steep potential, it's a weak pressure. Now, some two other comments. When you have gamma equal to 0, but you have pairwise interactions, again, you can show that there's an equation of state. I'm not going to write it here, but there's a closed expression for it. So you give me the pairwise interactions, you go to the bulk, you measure, there's a set of correlators that you have to know. You measure these, you know PM. Okay, so that's a special case. And actually pairwise interactions, for reasons that I hope will become clear, actually maintain many nice properties. If you have no torque, but you put aligning interactions, or quorum sensing, which we heard lectures about today, then there's no equation of state. Okay? So this I'm just throwing at you. I told you that I'll do everything for non-interacting, and I'll just quote results for the interacting case. Yeah, V of Ri minus Rj. Yes. Thank you. Yes. Yeah. Yeah. Okay. But not with a not with a potential VRI minus RJ. Okay, something that doesn't obey Newton's law. Okay? Yeah. Yeah. dt to 0. dr is finite. Yeah. If you put dr to so no rotational diffusion. So they're just moving in straight lines. Yeah, I don't. Is there 1 over dr? Did I miss the 1 over dr? It's fine. Yeah, it depends on the initial condition. Yeah, but I don't know even what it means. That you start with some orientation and they just move and they get stuck. Everyone's accumulated on the wall. Unless, yeah, everybody's stuck on the wall. Because I don't think that limit is, okay, it's a bit awkward. Yeah, okay, there's a really tiny approximation for most cases. Okay, sorry. Okay, next thing. So what I showed yesterday, I showed some consequence. I'm not going to return to the movies, but I showed you, for example, that if you put a partition with one potential on one side and another on the other, with a one potential on one side and another potential on the other side, then it will move in contrast to cases where you have an equation of state. Another neat example to think about is you take an active system and you confine it between two walls, one which is, say, very soft and one which is very steep, and you put your active system here. And of course, if you believe everything I've told you, then what should happen is that this guy will expand and the center of mass will move to the left, which is not a problem because we're not conserving momentum. If we conserved momentum, you would throw me out the window. Okay. Okay, so this is, again, moving by just changing chemistry and not realigning the bulk to do something dramatic. The bulk, I have to stress this, I haven't stressed it, the bulk is dead, boring, uniform, isotropic, nothing exciting is happening there. Okay, so you could think about why this happens, and there's a simple intuitive picture. And the thing is that you want to think, so we have a wall, and you want to think of one of these particles which is approaching the wall. So it's heading towards the wall, and it's clear this is an active force that's acting on the particle. If it's pushing inside the potential, then it's exerting a wall. It's exerting a force. But what happens when we have a torque, this guy is approaching the wall, and if it has a weak torque, then it's just rotating weakly and still staying inside the potential. But if I have a very steep wall, okay, let me draw a very steep wall, then this guy is approaching the wall, and the minute it hits the wall, it aligns parallel to the wall. So the particles are essentially exploring less inside the potential, so the torque is actually pushing them outside. It's rotating these arrows, and okay, I'll comment about this a bit later. So actually, if we're at that, you can imagine ellipses of this form. You could imagine ellipses which have the arrow pointing in the narrow direction, like humans, most humans, depending on the human, okay. Okay, and you can see immediately that in this case, a steep potential will lead to a pressure that's, thank you. If I have a steep potential and my arrow is pointing in this direction, it will cause the pressure to be increased, right? Because okay, so I have to go slower. Okay, because I hit the wall and the arrow is pointing this direction and I keep on, okay, that looks bad. Okay. 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 Okay, but I think now you get the message. Okay. Yes. Yeah, so there's definitely ordering near the wall. Whether this order is related to the existence of an equation of state or not, I'll get to later. It's actually not. Okay, there's always order next to the wall in active systems, so it's not directly related to that. Okay, and I'll show that explicitly. Okay, so given all these things, the question that I think everybody's poking me about is why in some cases we have an equation of state and in the other cases we don't have an equation of state. So what's the difference between the two cases? So difference between cases with equation of state and without. Okay, so that's one thing I sort of vow to myself to at least complete before I finish these lectures. There's also beautiful experiments by Olivier that were done. Hopefully he will discuss them. Okay? Okay, so before I go into this, there's sort of a small clause I want to open, which I think is interesting on its own. So obviously, any expression for the mechanical pressure involves the density of particles inside the potential. So it's useful to know a few things about how probability distributions of active particles look inside a potential. And there's been a whole industry of looking at these probability distributions. But I'm going to discuss here in class an extremely simple case. And many of the things that I'm going to say for this simple case just extend in a more complicated way to other situations. Okay, so before probability distributions of active particles. Okay, so I'm going to discuss a really, really simple model. So the model is it's run and tumble particles. Okay, in 1D. Okay, so run and tumble particles is sort of the 1D version of active Brownian particles. There's also two-dimension run and tumble particles, but that's immaterial to what I'm discussing here. These models have a really long history. They were studied initially by people like Howard Berg and Mark Schnitzer in the context of chemotaxis, and then lots of work was done by Julian here and other people. So let's consider the model. The model is very simple. We have particles that move to the right. So that's the analog of the arrow. So each particle has an arrow pointing to the right or left. Okay, so if you want, you could think about these as two kinds of particles. Okay, so particles with an arrow to the right move with velocity v to the right. Particles with arrow to the left move with velocity v to the left. And the analog of the active Brownian particle is that they flip between one another with rate alpha over 2. Okay, so sort of move, flip, not a very interesting life. Okay? And what I want to do is I want to study these in the presence of a potential. So let's write down the Fokker-Planck equation for this. Okay, so we have, this is the probability of right movers. Okay, so I'm writing down the Fokker-Planck equation. So I write down the current. So right movers move to the right with velocity v. I'm going to ignore, they don't diffuse. Okay? Yes? No, no, there's a clock. At any moment of time, it's flipping with probability alpha over 2 times dt. At any moment of time between t and t plus dt, if I want to be really precise. Okay, so it's an exponential clock. Okay, so it's moving to the right with velocity v, if it's a right mover. But then, if it's feeling a potential, then it's slowing down because of the potential. Okay, simple enough. But then it can flip. So I can lose particles with rate alpha over 2. And on the other hand, I can have left movers flipping into right movers with the same rate. Okay, and similarly, we can just quickly write the equations for the left movers. So this is left, and this is equal to minus dx. And the only dramatic difference is that I have a minus here. Okay, and then I exchange the roles of p plus and p minus in this non-conserving term. Okay, so that's simple enough model. It turns out that you can actually solve this guy exactly. So let me use the board here. Any questions so far about the model? Okay, so what I'm really interested is the density, and the density is rho, which is equal to p plus p minus. It's the total number of particles. You can convince yourself by summing these two equations in your head that that's a conserved quantity. Okay, so that's the density of particles. The other thing that I'll be slightly interested in is p plus minus p minus, which I could call the polarization. Okay, it's where the particles are pointing on average. So if it's 1, they're all pointing to the right. Okay? Good. So you can solve this. It's not a very lengthy calculation. You could do it on your own. And the solution is rho of x is equal to rho 0 e to the minus q. And q is equal to okay. So I'll let you copy this guy. Okay, so this is the solution for the probability distribution. And while you copy it, I just want to write down an equation that I won't actually solve, but I want to write down an equation for the polarization just to make a point later in a few minutes. Okay, so this is an exact solution of a very simple model for active particles in the presence of a potential. Okay. So now I want to make some observations. Sorry? Yes, everything is in a steady state. If I didn't say that, I should have said that. So this is steady state probability distribution. Okay, so all derivatives are equal to 0. Good. Okay, so the first thing is that if we look to leading order in V, so let's look at this expression. This is nothing. Log of 1 is 0. This 1 is gone. So we're left with this integral. This is a full derivative, which is proportional to V. Okay, so it looks like a Boltzmann distribution to leading order in V, but with an effective temperature, inverse temperature, which is alpha mu over V squared. Okay, so to leading order in V, Q is equal to alpha mu V squared times the potential. And the system is in equilibrium with a beta effective, which is 1 over T effective, the version of what I wrote before for this model, which is alpha mu over V squared. Okay, so that's actually a very useful thing to have, because if you want to look at things to leading order in V, then you could just borrow lots of stuff that you know, which is wonderful. And people have done that. Okay. When we look at higher orders in V, so higher orders in V. Okay, so the first thing is order V squared. Okay, yeah. Leading order in V that I keep first power of V. The first so I'm thinking as a, yeah, but okay, you could think about it in gradients, but it's the same thing. Okay, okay. Up to this subtlety, let me go on, okay? Okay, you're okay. So I'm looking to next order in V. So order V squared, I have this contribution from expanding the log. Okay, but that's a local term. Local term, which is not Boltzmann. Okay, so it's not, it doesn't look like e to the v anymore. There's a small correction, but it's still a local correction. The more interesting term is at order v cubed. And if I expand this, you can see that it's proportional. So in this case, q is proportional to this order. It has a term that looks as dx prime times dx prime v cubed. That's not a derivative of anything. Okay? So this term is inherently non-local. Okay? To know the probability distribution at a given point, I have to know the potential everywhere in the system. Okay? That's pretty strong. And I think that that's a very generic statement for these systems. You can actually, I'm going to leave it as a homework exercise. Okay, you can do the following exercise. So this is homework. Okay, so the homework is the following. Take the system, might as well put hard walls, I don't care, whatever you want, and put an asymmetric bump in the middle of the system. Okay, so it's a ratchet, one part of a ratchet. And solve the steady state. Okay, what you find out is that there's a different density on the right and left of the potential. Okay, So row right is larger than row left, and this is row left. Okay? There's actually an old experiment, not so old, 2007, okay, by from the Bob Austin group, where they take a bunch of E. coli and they put small funnels with openings at one side. Okay, and they throw a uniform density of bacteria inside. Okay, so I'll give you the reference. So it's Journal of Bacteriology. It's 189.870407. And what they observe is that in the long time limit, in the steady state, the density of bacteria on this side is much, much higher than the other side. So if you want, this is a toy model to the power of 4 of this. Okay, it's a really, really crude representation, but the physics is the same. We have a system that's breaking time reversal symmetry, and we put an asymmetric potential in the middle of the system, and the system shouts by pushing particles to one side. Okay, again, this is a local potential, but the effect is dramatic on the system. Okay, note that it appears at third order. So that's one advice for me. If you do calculation in these systems, always go to third order. Okay, that's where interesting stuff happens. Some of the interesting stuff. Yes? Okay, thank you. Okay, you could do the same exercise. Now I'm challenged to draw this thing asymmetrically. You could do the same thing with periodic boundary conditions. And what you'll find out is that there's a that's the standard old 30 years old, I don't know, 40, depending who you ask, ratchet current. So you find out that there's a current flowing inside the system. Okay? So generate current. Okay? And hopefully I'll get to discussing the relation between these currents and forces acting on these objects. So you can imagine that if I want to generate a current, I have to exert a force on the particles. And that gives some relation between the current and the force acting on objects. I'll get to that later in the talk. The last thing I want to emphasize is more for the sort of hardcore people who have followed some of the stuff on pressure. If you look to at delta, delta is non-zero even to order v to the power 1. Okay, you could see this easily by using this expression perturbatively. The leading order is Boltzmann. You plug in Boltzmann here, you can see that it's polar. Okay? So whenever you have these active systems and you have a potential, there's polar order developing. This has nothing to do with the existence of an equation of state or a non-existence of the equation of state. Okay, zero connection whatsoever. Okay, because some papers write that with confidence, but it's just wrong. Okay. Okay, good. So this is what I want you to remember, especially the non-local, because I think that hasn't been explored enough. Yes? Well, it's a recursive equation. Okay, you have to solve this equation to actually get delta. But I wanted to make the statement to leading order. Yes? They're generic. You could do perturbative calculations in V. Solving, for example, even this model with a diffusion of the center of mass, I'm not aware of an exact solution, even in 1D. I think I know how to do it. But, okay, I'm not sure it's worthwhile the effort. That's, okay, you have to balance things in life. Okay, so there's very few exact expressions for, so for example, in 2D, give me a potential, tell me what's the probability distribution. Okay, just hard, you could do it perturbatively. And even then, they're not very pleasant expressions because it's non-local. Okay, yeah. Yeah. No, 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 no. I think the slopes are. Yeah, we should talk. We're talking tomorrow after lunch. Yes. V2 power cube. Well, you see V squared when you change V to minus V doesn't change. So I think any asymmetry has to appear in the V cubed. Okay? But I don't have any gut feeling. I know from calculations, third order is where the action that I'm interested in many times is. Okay, other questions? Okay, great. So with this, just keep this in mind at the back of your mind. And now I'm going to go back, forget about these things. These are just general comments, which I thought might be nice to observe. And now I'm going to go back to the question that we were asking, why in some cases there is an equation of state, and why in some cases there's no equation of state. Now the bad news is this is slightly heavier computational-wise. The worst news is that we're late in the day. So you have to really stop me and ask questions. So what I want to do is address the question of when do we have an equation of state and why do we have an equation of state. Now, if you remember, one of the conclusions was that if we have momentum conservation, things look nicely. Okay, things are very, very simple. So what I want to do, I want to sort of hammer momentum and introduce momentum into our problem. So far we were looking at overdamped problems. So to have a clearer vision of what momentum is, I'm going to introduce an underdamped problem. Okay, so this will be, you do everything with overdamped, but it's sort of more transparent with the underdamped model. So underdamped active particles. So it's the same model, but just underdamped particles. Okay, so let me write down the equations of motion. So we have N non-interacting particles. So I equals 1 to N. Okay, and the equations of motion are the following. So Ri dot is equal to Vi. Okay, that's pretty intuitive. The velocity is the velocity. Okay, and then we have, if you want, Newton's equation. So mvi dot, and then we have a friction term. Sorry, I'm going to try to remember that it's a small v. We have a friction term. So this is the inverse mobility. Okay, we have the active force. So this is the active force whose magnitude is constant. Not sure why I have an I there, but too late. Okay, it's pointing The active force is pointing in the direction of the arrow that's assigned to the particle, theta I. Okay, so this is our old and beloved cosine theta, sine theta. We all know that guy. Then we have a force from the potential. And then we have the diffusion of the center of mass. So when you do everything correctly with fluctuation dissipation, this is the form of this equation. I think we saw it. Okay? Okay? My VI should be a small VI. Thank you. Please keep a close eye on these V's. Okay, and the last equation that we're missing is the equation for the angle degree of freedom. And again, we have our torque and we have our rotational diffusion. Okay, so this is torque and rotational diffusion. Okay? Sorry? Well, that's the form of the fluctuation dissipation. Okay, if you're confused, go to the overdamped limit and check things. Okay, and that will be more familiar to you. Well, this is the equilibrium term. So this is the guy that when we turn F to 0, we're back to equilibrium. Okay, thank you for that question. Okay, the model is clear? Okay, good. And why are they? Because I'm really interested in the momentum of the particles. We could do that. Okay? We could complicate things more. Okay, now really? Okay. Okay, good. So what I want to stress is by looking at this equation, no conservation of momentum. Everywhere, momentum is not conserved. This guy is not conserving momentum. This guy is not conserving momentum. This guy is not conserving momentum. Okay, so everywhere we look, there is no conservation of momentum. Okay, good. But nonetheless, I want to look at how momentum flows in the system. Okay? Okay, so we will see, that useful to look at momentum density. And density. Okay, so there are two fields which I want to write equations for. So I'm going to look at the density field, which is defined by sum over I of delta of R minus Ri. Okay, this is right now a fluctuating field. Okay, and the other quantity that I'm going to look is at the momentum density. The momentum density is the same thing with the MVI. Okay? So this is the density of momentum at a given point. Okay, and I'm going to denote averages in steady state. So rho of R will be the average of rho hat of R, just the same notation as before. and P of R, which is a vector, is the average. Okay, this is a vector of P hat of R in steady state. Okay, so how do we study these quantities? Well, we write down equations of motion for them. Yeah. Yeah, but it's not conserving momentum. This is friction, this is noise, right? This is the change in time of momentum. Yeah, but so again, you could have an equation of state in equilibrium irrespective of having momentum conservation, just from the fact that it's in equilibrium. Okay, it's not coupled to the other guy. Okay? So again, this is P dot. So no, 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 and actually this is also no. So nothing, sadly. Okay. Okay, so let's write down equations of motion for this guy. If you've seen these things before, it will be easy. If you haven't, then just follow me. Nothing's complicated, slightly lengthy expressions for this time of the day. Okay, so dt of rho hat of r. Well, we have to differentiate this guy. Okay, so we differentiate with respect to r dot, which depends on time, and then we take out the derivative outside. Okay, so we get that it's the sum of I of ri dot times the gradient with respect to ri of r of the delta function. Okay, just calculus. Okay, so that's, you probably saw this equation at some point in your past, or maybe not. Now it's the first time. So this I can identify with 1 over m times the momentum density, and I flipped this gradient to be with respect to r instead of with respect to ri. Okay? Everybody with me? Some of you look like you're about to commit suicide. Okay. Please stop. Okay. So okay. So the next term is like epsilon more complicated, because now we're differentiating this guy. We have to differentiate this guy, and then this guy we have to differentiate as before. Yeah. Steady state, thermal average, but I'm not there yet. Okay. Okay, good. So we have sum over I m vi dot times delta of r minus ri, right? I've differentiated this guy. And then we have the next term, which is essentially this guy, mvi, and that's times vi dot the gradient with respect, I'll keep it with respect to ri at the moment, times delta of r minus ri, and I'm going to flip it as before with a minus sign. Okay, so this guy I'll turn into a gradient with respect to r with a minus outside. Okay, so that's some progress, almost. And now this guy we know. This guy is specified by this equation. Okay, a bit lengthy for this time of the day, so I'm going to take all these terms, okay, everything here, and I'm going to plug it here. Okay, so that's what I'm going to do. And when you do that, okay, I'll skip one line of math. Okay, if the gamma is confusing, it's because I haven't finished defining things, so bear with me. Okay, so I haven't, so this is one equation, and this is another equation, which looks silly at the moment because many of the terms are undefined. Okay, so, so first of all, gamma is equal to gamma tilde over m. Okay, that's just redefining gamma theta. Remember, I replaced it here. So this comes from the gamma tilde v, and the m, we fixed it. Okay? The other term comes from this guy that I'm going to define in a second. The other term comes from this guy, which I'm going to write as J, which is a rank 2 tensor. Okay, so this is a tensor multiplication. So just to make this crystal clear, J alpha beta is equal to M VI alpha VI beta R minus RI. So those of you with the right background recognize this guy. Okay, and the other term that's a bit of a mystery is this guy. Okay, and it's defined in the following way: the square root of 2 dt rho hat, where rho hat, remember, it's this guy, okay, times lambda is equal to sum over I of square root of dt times eta I of delta of r minus ri. Okay, so it's a sum over all the noises. And what I'm leaving for you to check is that lambda alpha at RT, lambda beta at R prime T is equal to delta alpha beta, delta R minus R prime, delta T minus T prime. Okay, so it looks a bit scary, but let me guide you through term by term. Okay? So this guy is just losing momentum to the surface. It's just this guy. This guy is losing momentum to the potential. Okay? So this is this guy. This guy is the active force pumping in momentum. This guy is the noise. And this guy, if you remember from the first talk, this guy is just a flux of momentum, MVV. Okay, and it's now a tensor, but I actually won't worry about it being a tensor later. Okay, so this is what the equation does. This is the flux of momentum, and this is all these other terms which are pumping momentum into the system. Yes? Okay, so that's your homework. Okay? Could be. That's your homework. Okay? Okay, good. Okay, so we have our equation. And if you look at this equation, there's only one term that's conserving anything. It's this guy, because that's the momentum moving from one side to the other, so that's the trivially conserving guy. So only this guy is conserving momentum. Kill, 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 kill. Okay? Good. So what I want to do now is look at the, derive the equation of state using this. Okay, so it's not You can see where I'm going because I have the rho grad V. Rho grad V is a good thing, right? Why is it a good thing? Because that's almost the definition of pressure. We only have to take a thermal average and integrate over space. Okay, good. Questions? No, I'm not going to do that. Okay? No, we don't need that. Okay, so what I want to do is I'm going to look at a very simple simple geometry. Okay, so I'm going to look at it's a two-dimensional system between two walls. So there's V of x minus L of V of x. And just to keep the notation simple, I'm going to, so this system has periodic boundary conditions in the y direction. Okay, so x hat and y hat. So we have periodic boundary conditions in the y hat direction. And to make my life even easier, and because I'm a theoretician, I'm going to set the length of the system in the y direction to be 1 in my units. Okay, you could put in L's and then you'll have L everywhere, but I don't want to deal with that. Okay, so the setup is clear. Just a simple what we were looking at before, but with this underdamped system. Okay, good. So now define rho of x. Okay, this is really, I could have cheated and skipped this, but I'm sort of being overly pedantic. So this is the density of particles integrated over my system of size 1. Okay, so it depends only on x. We have translational symmetry with respect to y, so I'm getting rid of that. So densities depend on on x. Okay, and I'm going to look at the steady state. Okay, now check that I'm not talking to myself completely. What's the average of P in this setup? I'm talking to myself. Yeah. This is momentum. I'm putting the system, we have translation and invariant in this direction. So is there going to be a flow in this direction? No. Okay, walls here. Is there going to be a flow in this direction? No. Okay. So 0. Okay? Okay, so the average momentum, when I take a steady state average, the time derivative is 0. And the average of this guy is 0. So I'm left with the rest of the equation. Okay? The average of this guy is 0. Okay, people were hesitating. Should I say 0? Okay, the average of this guy is 0 because it's a white noise. And I'm doing Ito if you want to be really pedantic, yes. Okay, we'll get to Ito soon. Okay. Until what time do I have? Okay, soon Ito. Okay, good. Okay, so I'm going to use that. So I'm just copying this equation with angular brackets and getting rid of this guy and this guy. So I have, using this, we have 0 is equal to minus rho of x gradient of v. It's really only in the x direction, this guy. So the gradient is a bit of an overkill. Plus the average of I, fi cosine theta I. Okay, so this is the active forces pumping in momentum, if you want. And then we have minus, we're now right in really, okay, I should really take this to be dx because we have only the x direction, and then we have dx of the average of jxx. Okay, so you could think about this as a force balance equation. Okay, remember in the talk yesterday, it's all very vague, I know, but in the talk yesterday, we had that the force balance was the derivative of the momentum flux equal to the force exerted by the wall. Now we have these active forces pumping in momentum into the system. So they're doing something extra. So the force balance has these two regular terms, but this extra special guy. Okay? Good. So now I'm almost there if you're desperate. So I'm taking this to the other side, integrating over x, and lo and behold, I have an expression for the mechanical pressure. Okay, so Pm is equal to the integral of rho of x dxv dx, and I'm going to take it from 0 to infinity, and this is somewhere in the bulk of the system. Okay, this guy is a full derivative. This is the flux of momentum. Remember? mvv. Okay? So this guy is giving me the average of jxx at, so this is 0, at 0. So you recognize this guy. This is what we had when we had just momentum conservation. But now, active particles come in, and we have this average. Okay, so this guy is an equation of state term. Okay, it's a nice, depends only on the bulk. This guy doesn't look like it. Okay, so we could throw our hands up and say, okay, no equation of state, but then we remember that I've shown you in an example that there are cases where there is an equation of state. So something interesting must be hiding in this term. Okay, specifically, what I'm going to show you is that when there's no torques in the system, this guy can be written as a divergence of something new. And that something new, we'll have to understand what it is. And that would be our extra conservation law. Okay, that will be the new quantity that will be conserved. Now it's conserved in a really, really restricted sense of the word. Why I'm sort of rushing ahead, I'll repeat it later. Because this is all in steady state. So it's sort of a conservation, it's not really conservation law. If I look at the equations for a steady state, it looks like a conservation. Okay, it relies on this geometry actually, because I put P equals 0. And I just told you that when I do funny things, I get currents. Okay? But I'm still going to go ahead with that. Okay? Yes? This is non-interacting, nothing there's no mechanism. Dissipative. If you find vortices, I'm recorded. $100,000. Okay? Not transient vortices. I'm probably getting a divorce from my wife as we speak. Yes. Just a point in the bulk. Okay? The mo. Yeah, that's Ito. Yeah, but that's Ito because this is, okay, this is our Ito convention. So Ito guarantees that this is 0. Okay? Okay, good. So something interesting is hiding in this guy. So I have to calculate this guy and express it in a different way. Good. So to do that, I have to do a small pause. You're looking at me terrified. And teach you something about Ito calculus. Yes. Well, I haven't done anything illegal with Ito. Soon I will do a legal thing, but I have to teach you Ito. Okay? Okay, so just to summarize, something hiding here. Okay, so we want to re-express this guy. So to do that, I have to do a small mathematical, really sloppy. If you're mathematically pedantic, close your eyes. Okay, and I'm going to do a bit of Ito calculus. Okay. So this is math break. Okay, and I'm not going to teach it on this full equation. I'm going to look at a stochastic differential equation in one dimension, which is of this form. Okay, so I'll define the noise. So the noise is our usual Gaussian white noise. Okay, so it's drawn from a Gaussian distribution. And when I say Ito, I mean that this is at t, and this is between t and t plus dt. Okay, so these are uncorrelated. This guy is kicking in this interval, and this guy is at time t. Okay, so that's what people call the Ito convention. There are other conventions. I could choose this time, this term to be at time t plus dt, and at time t and some average of them. Okay, and you could do more complicated things. The one that I mentioned a second ago is called Slatanovich. Okay, but here we're dealing with Ito. Okay, so the question that you asked, and I was alluded to a second ago, okay, I'm not getting there yet, but for average, we know that the average of dx dt, well, the average of this guy is 0, right? Because of the, if you want, because of the Ito convention. So the average of this guy is just the average of this guy. So this is the equation for the average of dx dt. So if this guy is a linear function, then you can solve it exactly. If it's a nonlinear function, then it's a hierarchy of the like that we saw in Olivier's talk, for example. So you have to close it at some point. Mean field would be replacing this guy by a of average of x. That's what we call mean field. Okay, just a small comment. Okay, good. So the question I want to ask, this is too small, right? I sort of didn't plan my board well. Okay, I'll do it over there. Okay, so the question is, given some function of x of t, what's the equation for df of x of t dt? Okay, what's the differential equation for this guy? Okay, so it looks like a stupid question. Okay, if you know it, it's not stupid. But if you don't know it, it looks like a silly question. Because what you would guess is that what I would do, I would just do df dx, dx dt, and then I would do df dx times a of x. Okay, seems plausible, but this is wrong. Okay, this is just, you can't do that. Yeah. Yeah, but x is changing in a stochastic manner, so you have to average over the histories. Okay? Okay, so this is all wrong, and that was pointed out by Ito, I don't know, 50 something? 44, somebody knows the year? Anyway, became famous. Okay, and what I want to do is to give you the correct equation, how you fix that. Okay, so to fix, now I have 6 minutes to finish this. I'm going to write dx is equal to a of x times dt. So I'm just writing dx to order dt. But now we have our white noise. So it's b of x of t. But then we have the, remember, this is the Ito convention. But then we have eta of t prime dt prime. So I've been more careful about this guy. I'm integrating over this noise term. Now this is, right, this is how we get Brownian motion. So what's the size of this integral, the typical size of this guy? Square root of dt. Okay, so that's why we have to be careful. Because this equation has a dt and something of order square root of dt. So when we expand things, we have to be careful. Okay? So let's do that in the time that we have left. Okay, so what I'm going to do, I'm going to look at df of x of t. Okay, so that's easy enough. X of t plus dx minus f of x of t. Okay, that's what we mean when we write that. Okay, so now remember dx has a term that's of order dt, but then this guy has also a term of order dt squared, square root of dt. Okay, so I better expand carefully to second order, keeping this guy. And that will be the non-trivial term. Okay, so when you do that, you have f prime of x of t times d x of t. And then I'm keeping, that's what I said a second ago, the second order term, because I'm worried about this eta squared term. Of course, we have higher order terms. Okay, so now let's replace this guy keeping the order dt. Okay. And okay, let me write everything down. It will be, I think, clearer than me mumbling. Okay, and then we have our second order term. And the only term that I'm keeping here is the eta square term. Okay, why only the eta square term? Okay, because this guy square is what? dt squared. We don't care about that. Okay, so I'm keeping only things to order dt. Okay, now I take a thermal average, and I'm assuming you know how to take the thermal average of this guy, and we're left with df of x of t dt is equal to a of x times f prime of x. This is what you guess if you know calculus. Okay? But then we have this extra new term, which is b squared of x times the second derivative of f with respect to x. Okay? So this is a non-trivial term. So this is known. There's also a stochastic version of this equation, which I'm not deriving now. I don't need it. And this is called the Ito formula. Okay, and it's a good thing to remember. At least for me. Okay. I don't think my kids need it yet. Okay. Okay, so so I think I have 1 minute, and I'm not going to do anything in this 1 minute. So what I am going to do tomorrow, first thing on the morning, you're not giving me a lot of motivation, but okay, I have to ride with what I have. Okay, what I'm going to do, we had this pressure was equal to the momentum flux plus this extra term. I'm going to calculate this extra term with Ito calculus, and I'm going to break it into a term which is conserving something, which I'm going to discuss tomorrow, plus a term that's non-zero only if you have torques. Okay, and this guy we'll see will be sources, will be acting like sources of momentum at the wall, and I'll show you one graph of numerics. Okay, so see you tomorrow.